Hi, this is a brief supplementary lecture on control charts for the Executive Black Belt / Green Belt class, and this is really just to introduce you to a concept called the control chart, which you undoubtedly heard of. We'll talk about what are some of the uses of that. We'll keep this a fairly short lecture. I'm going to try to anyway, and just to diagram out some things. We'll talk about how to use a control chart, and we'll talk about the primary control chart that I want you to have in your arsenal, and that is the individuals chart or eye chart. So that's the thing that I really want to talk through. By the end of this, we'll be able to assess a process stability using a control chart, and that's really my goal, is really to talk about how do we determine whether we have a stable process or not. Control chart is an unfortunate misnomer because it doesn't control anything. It's a stability chart is maybe the way that I would like to look at it. Or Don Wheeler, who is, I'm a follower of his view of control charts, a statistician from out west, does a considerable writing on control charts, questions the classical uses of control charts. I'm actually in his camp, and I think that from a number of perspectives you're going to find that this is the right control chart to try and use. Certainly from a people perspective, it's the easiest control chart to implement, and it is effective. So that's about as close to perfection as you can get, implementable and effective. We'll also describe a few typical patterns. I don't want to get too much into that. I want you to look for one particular pattern first, master that, and then we'll talk about some of the others as well. Okay. So the first concept I want us to understand and to get through is special and common cause, and why we would use a control chart. So let's take a look at that. Let's do a little blackboard exercise. And first of all, I want us to understand sort of where the control chart comes in. So a control chart, we know that. Oh my goodness. Let's make them smiley. Okay, so we know that when we did the SIPOC, we've got customers and we've got a process, right? And our customers can be internal or external or whatever. And the whole key is to kind of figure out at that boundary, right, getting things right from our perspective and getting them lined up to what the customer wants is huge, okay? So the measurements that we get out of a process are what are called our KOVs, our key output variables. We also call these Ys, or outputs, okay? And it turns out that it's important to have both views, and when we do a baseline, it consists of two parts. Baselining is going to consist of two parts, and the first part is stability. We're going to assess stability. That comes from a process perspective. So stability is a process or inward, got to spell it right, an inward-looking thing. We can't just do stability, but it's important because it can help us understand whether we're capable of meeting certain things. Stability perspective, and then we also want to look at it from the customer's perspective, which is called capability. See if I spell that? Which is essentially this percentage of time we meet requirements. This is a little bit different. This is a different question. This is really asking, is the process with respect to, that's WRT, the KOV, erratic or not? That's the real question there. And the interesting thing is, we use different things to assess this. Here we essentially have lines drawn and we see, are they in or out? Here we do the same thing, but the lines are drawn with something different. And that's important to note. They're drawn with the process data. Okay? It's going to turn out that Again, if this is our process, here's our customer. Right? This is our VOC, this is our VOP, our voice of process. That what we do to assess stability is we look at a time series chart. We look at our process as it evolves over time, our KOV as it evolves over time. This is a time series chart. Okay. With our voice of customer, we essentially take a different view. We use a different picture. Remember the plot the data? We look at, say, a histogram with a line drawn for a customer spec. Maybe I should draw it in a different color because customer specs are often confused with something that we're going to be talking about. I'm going to draw it in blue. Okay, and we might say, what is the percentage that's above that percent bad? Like if it's cycle time, for example, this would be bad. Long cycle times are generally bad for the customer. Okay? All right. Over here, what we're going to do is we're going to draw, we're not just going to draw them, we're going to calculate them from the data. We're going to draw these, and these are going to be our control limits. Again, I wish they were called process behavior limits or stability limits or something, because they don't control anything. And these come from process data. We calculate them from process data. So this helps us understand whether a process is stable or whether it's not. And this comes from something else entirely. This comes from the customer or from management. Or from, you can think of it as coming from Mount Olympus if you want. That's a reasonable way of thinking about it. Thunderbolt from Mount Olympus says, "Thou shalt not have a cycle time greater than 5. Well, the process actually dictates what actually does happen, but this is what the customer wants. You see the difference? So we need to do both. We assess the voice of process first that says how stable is our process, and then we assess the voice of customer. The piece, so that's how we do a baseline, and we'll have more on that in a later section. But we're going to be focused today on this, and this is called a control chart. A control chart differs from a time series plot in that it has these red lines on it. We'll understand what those red lines are. Here's, in a nutshell, what they are, what they do for you. We are really good at seeing all kinds of patterns. Humans are excellent at it. A control chart helps us filter and says, is that really a pattern? Yeah? No? Is that really that rare? Or is it not? So first let's talk about special and common cause, and let's do that on the blackboard here. This is special and common cause variation. Okay, this is time, and this is our KOV, key output variable. So imagine that we, in our process of, say, measuring the wait time, let's go back to our restaurant example where we had the KOV was the cycle time, and that was the time that it took the restaurant to bring the food to the different customers' tables. And let's say that what we did was we went out and we sampled, I don't know, maybe 3 times a day at irregular intervals. And we got something that looked like this. In this case, high is bad, right? Okay, so if you ask somebody, oh, what would you do if you were confronted with a data point like this? Okay, normally they're delivering within this time, sometimes a little less, sometimes a little more, and then bam, what would you do? I think most people would say, well, we fix it. Dig into it. Who's the waiter? What was the cook? Was anything going on with the oven at that time? We don't know. Okay, let's suppose that whatever happened, it was back in control or back stable again. And then you got a data point like this. Now, if I asked you, what would you do here? I think people are about 50-50. Some people would say do something. Some people would say don't do something. And then finally, what would happen if we went to this data point right there? And I think most people would say, no, at this point, there's nothing really super special about this data point. I mean, it could be about the same as this. So this would probably be, yeah, this is not special. Let's just put it that way. This is not special. Okay, so the point of this is that when I draw what are called these red lines, and I'm going to draw them with dashes, best I can. The red lines help us understand what is special and what is not. So it's kind of like an operational definition of what special cause means. So special cause points are these points that are out of the red lines. Common cause are the points that are inside. Okay? So every process has common cause variation. That means every process varies normally in some sort of way. Some processes also have, in fact many processes, also have special cause variation. From a practical point of view, what that means is is if we're running an ordinary everyday process, we're going to try and go out and figure out what's wrong with these. These are special cause. It's worth our time and effort to try and fix them or to try and figure out what they are. But for these, if we're just in an operations mode, it's not worth our effort to just go out and try and fix them. Okay? That's the difference between these two points of view, is that in one case, you're willing to go out and do that. In the other, you're not, unless you have a special project that's willing to take on the whole process and to look at it from a much deeper view. So the control chart can help you stop firefighting when you're wasting capacity digging into what happened on this week to make it so high, or what happened on this week. The answer is it isn't that high, so let's not dig into it all that much. It really doesn't differ that much. Now remember, this is only half of the view. It still all could be bad. All these things could be bad, which means we have to do something about it from the customer perspective. But this essentially tells us when we can do a quick fix and when a quick fix is not going to be enough. For this particular point, if this were a problem, if we fixed it, we're not expecting that to necessarily come back. This looks like it was a one-off. But for this, if this were a bad point and a problem, again, I'm not saying that it is. We don't know the customer specs. But we only know the control limits, not the same thing. So if this were a problem, then we would have to address it in a much more serious nature than just a quick fix, because there are lots of other times that it's creeping back, and we need to figure out all of those things, not just that one particular point. Okay, so that's the backdrop. That's the backdrop for this. Okay, here's where you can use, as you're picking this up, this is on slide 62. Here's where you can use control charts, or the most typical places to use control charts are when you're baselining and when you're monitoring at the end, putting together your control plan. They're fantastic to use as management tools as opposed to, look, if you're just starting on your metrics and you're collecting metrics, wonderful. Keep going on that. If you haven't yet visualized them, start using time series charts. Okay? So much more powerful to look at it with your eye than a number on a spreadsheet. And even red, yellow, green. Generally speaking, people overreact or underreact to those types of things. If you can go the distance, get the control charts on there. So move to them in pieces. Okay, we just talked about stability and capability. I'm not going to talk about this anymore. The interesting thing is that, again, I want to repeat that many people think, oh, this is an out-of-control process, or this is such an unstable process when they think about anything. Remember, we're talking about, is it what I would call a stable process? Is it stable with respect to that key output variable? And in a surprising number of times, you'll find that it is stable. It's just not very good. So if you don't know what you're doing, a lot of times it's a stable process because from the point of view of the customer, it's predictable that you're going to get bad results out of it. Either way, that's a bad thing. Very quickly, control charts were developed by Walter Schuhart in the 1920s. One of these giants in modern of now I guess it's getting old statistics, but giants of statistics. They've been around for a long time. He did not invent the chart that we're going to look at, which is the I chart. He invented the P chart first. The I chart was invented in the 40s. I chart is a much more flexible tool, but Schuhart invented essentially the whole methodology of looking at these. Here's what a control chart looks like, and we've been advertising that. It's a time series chart, so here it shows over time. Maybe that's day 1, day 2, day 3, day 4, day 5, etc. You're measuring your KOV repeatedly, and you're seeing how that varies over time, and you see sometimes it's up, sometimes it's down, and so forth. That's those points. We've also added some doodads in here. The green line at the center is the mean. The plus or minus 3. The red lines are set from the data. Remember, it comes from the data, and that's such an important thing to keep in mind. It comes from the data. Whoops, that's not what I wanted. Let's go here. It comes from the data. Exclaim. Okay? Please. Make sure that you understand these are not set anywhere you want. They come from the data. All right. And they're set at plus or minus 3 standard deviations. So just a quick why. Why did Walter Schuhart choose plus or minus 3 standard deviations? Well, the reason he did was essentially comes from the normal distribution. And it turns out that if you look at a normal distribution, the area inside the normal distribution, okay, if you're within plus or minus 1 standard deviation from the mean, if this is our mean, right, I'm going to call that the mean, mu. If you're wondering why it's all Greek to you, that's it. Okay, I'm using Greek letters. Plus or minus 1 standard deviation would be the red hatching that I've got right there. Okay. That's 68% of the data. You see that? 60. Now I've just scratched it out. That was brilliant of me. There. 60, and that's better. 68% of the data fall within plus or minus 1 standard deviation. Within plus or minus 2 standard deviations, and I'll red hatch that, but in the other way, we get 95% of the, I'm just going to write that in now, that's 95% of the data are within plus or minus 2 standard deviations, and within plus or minus 3 standard, yes, so that's plus or minus 2 standard deviations all the way out to that. There we go. And within plus or minus 3 standard deviations, which is all of this, let's see if I can do a really super fancy thing and put in blue or something like that. There we go. Within plus or minus 3 standard deviations, and I'll kind of do this whole thing and color it. I'm having way too much fun here, I think you can tell. Then plus or minus 3 standard deviations, 99.7% of the data fall there. So the point is, going back to our control chart, if we look at our control chart and the control and the process is in control or it's stable, we should only get 3 out of 1,000 points that are outside of that plus or minus 3 standard deviations. And therefore, when we see something that's outside of that plus or minus 3 standard deviations, that tells us we need to go check it out. That is something, that is a signal that's not normal about this process. It's not normal operations. Therefore, it's important for us to go check it out. It tells us point of instability, out of control. Okay? Now, it can be out of control good. It can be out of control bad, right? So out of control good would be for a sales process to go through the roof. Out of control bad would be for a cycle time to go through the roof, right? Okay, got it. So it does vary. Here's a classical control chart picker. All I really want to say about this at this point is we'll cover some of these other charts, the P chart, the MP chart, the C chart, the U chart, the X bar R and the X bar S. By the way, this only still scratches the surface. These are just the main ones, the main what are called Schuhart charts. We are going to focus on the individual control chart. And Don Wheeler, this fellow I talked to about before, it turns out he looked at all sorts of other distributions of underlying data, including many non-normal distributions and really non-normal distributions, and found that in almost all the cases, I think it was 99% of the cases, the individual's chart was giving what would be a correct action, and so therefore ought to be a chart that one could use. Okay, let's talk about the chart rules. The only chart rule that I want you to get right now is if a point is outside the plus or minus 3 standard deviation limits, we want to investigate it for special cause. Otherwise, we don't. Now, that doesn't mean we don't do anything. It might mean that we have a project and we have to improve something, and we'll talk about that near the end. But it does mean that you can't do a quick fix. Okay, if you don't have stuff that's really out of control, points that are outside those 3 standard deviation limits, quick fixes probably are not going to work well. Okay, let's talk about the control chart. And these are appropriate for lots of different things. Essentially, anytime you have a continuous or numerical key output variable. Okay, anytime you have a numerical key output variable, pretty much then you can use an individual's chart. They're characterized by single data points. They're not average. That makes it easy to use on the plant floor or in the office because the measurement is the point of data that actually goes on the chart. Very, very helpful. When you're averaging things or you're doing math before you put that data point on the chart, or even when you're looking at it from management, it makes it more esoteric and more abstract and farther away from the action. It's definitely the easiest chart to use, and it's probably the best chart in many cases. Second thing is it represents the customer experience as well, and we'll talk a little bit more about that later when we talk about some of the mechanics. But let's just get some of the main stuff down. So let's go through an example. This one happens to be product demand. I'm going to do this in 2 ways. I'm going to do it first of all using Excel statistics, and then doing Minitab. You'll see that Minitab is much simpler. The price you pay is has all these other bells and whistles. It's like going to a Las Vegas. If you're a statistician, it's like going to a casino and seeing all these lights going off and all that kind of stuff. All right, so let's do this in Excel statistics. Start out with that. First thing I need to do is I need to open up the file. I've got open Excel statistics right here, but I need to open up my data file, which I thought I had open, but apparently I don't. Okay, which is called product demand. Now you should recognize this, seen this before. Okay, here we go. So let's do it in Excel statistics first. And you would think that it works exactly like all the Excel statistics. You choose it, you select it just like the one num, and you're done. It'd be wonderful if it did. Unfortunately, it doesn't. I wish that it did. Sorry, folks, it doesn't. By the way, we can look at this. Here's the time series plot. First guess might be, if we look at this, I think this is worth the time, by the way, to take. If we were just doing a time series plot, the first guess would be, I think most people would say, yeah, it looks pretty stable. It doesn't look like it's going anywhere. However, we're all humans, right? So we start, the longer that we stare about it, we see things like, look at that one. I wonder why that point is so, let me go in red, because red is more, yeah, do it. Yeah, that looks like it's a little bit low. Better get sales up. What happened that week or that month? Or what, let's say it's weekly. Can you imagine being in this set of weeks? Oh my God, sales are dropping. How about this one? Sales seem to be really extra stable. Or this, sales seem to be growing. All of those are patterns that humans pick up. The question is, are they real patterns, or are they patterns that are just in our imagination? We have good imaginations. Our imaginations are great for finding new things, and for identifying new ways of doing things, and for developing new products, and for writing great mystery novels. What they aren't good at is for helping us understand how to use our capacity in staff and in resource, well, if we jump at things that are ghosts and deck our capacity or deck up our capacity to beating down these things that don't really exist, we're simply wasting it. So a control chart can help us understand whether these are patterns or whether they aren't and what we need to do about them. Okay? That's the power of a control chart. All right, back to business here. Let's take a look at our data. I'm going to close up the one num. Let's take a look at it. Here's how we do a control chart in Excel statistics. First of all, you have to go to control first. Okay, open up the control worksheet. Click on numerical. We're looking at numbers data. And there's our little eye chart you see down there on that tab. But we have to get the data in first. And if we go here, see that there's our data. Now, if you recall, you can double-click on anything that's red, and this is actually going to be helpful. If you double-click on data, you can clear the data from it, and that's helpful. Or you can just clear yourself doing this. Either one, doing a selection and clearing it out. That's what I'm going to do. Okay, now we have to paste the data in. It's important that we paste it just as it is. So I'm going to select it. Notice I'm not selecting the row. If I select the row, it won't work, unfortunately. Back in the control, and back control. And there it is. And you know you got it right is if it fills in all the other stuff there. Let's take a look at our control chart. You should recognize this. It looks a lot like our chart that we had before. And we can tell, at least fairly quickly, this is a process that's stable. We have no points that are outside those plus or minus 3 limits. And in fact, why were sales so low is like asking why these sales were so low. It's not that different. And so it's not that low relative to, it's something that you might expect every once in a while. Does that mean it's good? No, it doesn't mean that it's good. If you have a problem with this process and you need to shift it, that's a project. You can't simply look to single data points and figure out what you need to be doing. Okay? This is a stable process. Now I do want to do it in Minitab very quickly. We'll do the same thing in Minitab, just to show you where it is. We're going to have to do the same thing. We're going to have to copy and paste. This time we can use the whole thing there. Oh, wait, I already had pasted it in. That's interesting. Oh, I see. I've got too many tabs open. There we go. Well, let me just paste it in. Bam. Okay, so now you see I've actually done it. There it is. Okay, let's go to Minitab. The control charts happen to be in Stat, Control Charts. And now, look, just to give you an example of all the stuff that's in there, and you can go into, there's the Box-Cox transformation. Let's not go there. Subgroups, sounds like Chinese food. Individuals, there we go. We're getting in the right place. Individuals chart. That's what we want, okay? Control charts, variables for individuals, individuals. And go ahead and select demand. Click Okie dokie. And our control chart's done. You'll see it's the same control chart. Now, I'm also going to show you, if you go into iChart options, there's also, statisticians have developed all sorts of other tests to look for patterns in our data. Let me cancel this. I want to move this over. There we go. To look for all sorts of patterns in our data, there's other tests that we can use. So here's our 1 and 3 standard deviations, outside of 3 plus or minus 3 standard deviations. They've made it really easy to read by not numbering them and by putting K instead of the number. That's really helpful. Not really. Okay, 1 point outside of 3 standard deviations. That's the one that we've been using. But there's other data points. There's other patterns. Like here's 9 points on the same side of the mean. So that would be something like flipping a coin and getting 9 heads in a row. Certainly is unlikely. Here's one that I like, which is 6 points all in a row decreasing. And they're all set so that about 3 times in 1,000 you would expect to see that pattern. Okay, let's go ahead and turn on all those tests. I'm not going to go through all those tests, but let's turn all those tests on. I don't know why it Oh, I see. Let's turn on all the tests. There we go. Turn on all the tests. And let's see what happens. See, even with all the mini-tab tests on, it's still saying no pattern there, no pattern there, no pattern there. Definitely not special cause there. So it's not finding any. This is a stable process. Okay. So I think the first and probably the one of the most important things to keep in mind is that processes are generally speaking more stable than you think. Okay? So our brain is really good at finding those patterns, is really bad at understanding that those patterns are perhaps just figments of our imagination. Okay. Let's go back to our example. Okay, and that just says what it is. Let's look at a different one. This one happens to be for on-time services. So here we've got a company that turns on services for its customers. Could be a bank, could be a healthcare plan, like it's starting you as an employee. How long does it take to get you signed up and all that? Okay. It could be a hospital. How long does it take you to admit? It could be a manufacturing process. How long does it take us to fulfill an order? All of those are basically the same. And here we're looking at OTS, on-time service, which and in each individual one is a yes or no. So that would be binary or categorical. But what they're doing is they're pulling 100 of these things, and they're looking at 100 of them and saying, well, what's our percentage of these coin flips, essentially, of these yes or no's that we actually got on time? So that's what that is, OTS. And that is a num. We'll see the difference when we look at this. Now, classically, this would be done in a P chart, but we're going to use P chart is classical. If you go through that control chart picker and you want to, you'll find it. But we're going to use my chart, which I think will be very helpful. Okay, so let's go ahead and open up the data file for that. On-time services. Open that up and aha, okay. So here we've got on-time services. Here's the number on time. We want to look at the proportion on time, proportion OTS. Now, if this, especially we want to do that if this number, if this, sometimes they pulled 100, sometimes they pulled 150, we definitely would want to divide this by this to have a common ratio. But now you get the whole point, is that each one of these accounts, each one of these 100 accounts is a binary. Yes, it was met. No, it wasn't. But in total, they make a numeric variable, which is kind of nice. Okay, so let's take a look at the proportion OTS. Remember, we've got to have that control open. Let's go to the data. Let's clear out the data. Done. Cleared out. Okay, let's go back to our on-time services now. And I'm going to make what I hope is an instructive mistake here. First of all, let's copy the data and let's paste it in. Okay, here's my instructive mistake. If I just paste the data, look what happens. Yeah, I can't do this because I copied something that was actually a formula. So in Excel, that's not going to help me. So I've got to instead copy it as and paste it in a different way. I've got to do a paste special, and I'm going to paste the values. There we go. Now the values are pasted. I've got 20 of them. Let's go to our eye chart, and holy moly, there we go. It looks like if we're looking at this control chart, we would want to investigate this one for special cause. Okay? Simple as that. Now, the other question that might be helpful for you is to say, well, what happens if I want to take this out? Because think about it. If I take this special cause out, then my estimate for my plus or minus 3 sigma is going to be tighter, right? And, you know, we haven't talked about how that estimate is made, and I do want to talk about that just quickly. It's called the moving range. So the moving range, because these are individual charts, what the moving range does is it takes successive data points and subtracts them and estimates the spread of the data that way. When the process is in control, it turns out, yep, that's just fine. When it's not, it turns out that that the standard deviation differs quite a bit from the moving range. And that's okay. That's exactly what we want to have happen. But it does mean that when we find an outlier, we're probably going to want to filter that out to get the true limits a little bit better. So let me first show you the mechanics of how that moving range works. Okay, I'm going to show you the mechanics for how the moving range works. So let's suppose that we had a process that looked like this, and I'm going to be, let's suppose that this is 5, this is 0, and this is 10. Okay, and here are some of the points that I've got. Okay. Okay, so let's suppose that's a 6, and that is a 3, and that is a 5.5, and that is a 3, and that is a 6, and that is a 7, and that is a 2.5. Okay, got it? So what we can do is we can write down, let's see, this is point 1, 2, 3, 4, 5, 6, 7, 7 points. And here are their values. I'm going to call those KOV. Here are the values. Some people call them X. Okay, and here's what I'm going to call is the moving range, the MR. Now, this is the only time you're going to see this, so it's not a big deal if you don't get it. For the green belts that are out there, you don't need to know this. This is something that any real computer program that's doing control charts will have in it. If you're a black belt, you need to know just a little bit about this. So we're going to go through and do it. So here my KOV is 6. I'm going to write all these down. Then a 3, then a 5.5, then a 3, then a 6, then a 7, and then a 2.5. Right? Now here's what the moving range is. The moving range is the difference between the specific data point and the point that preceded it. So here we can't do anything about it. Nothing there. On this one, however, this is equal to 3 minus 6, which is negative 3, but we only use positives. So the moving range here is 3. Got it? 3 minus 6 is minus 3, but we just use the absolute value. This one is 5.5 minus 3, so the moving range here is 2.5. Here this is 3 minus 5.5, which is minus 2.5. Again, we just write down the positive of this. Again, you see that? 3 minus 5.5. This is 6 minus 3, which is 3. This is 7 minus 6, which is 1. And this is 2.5 minus 7, which is 4.5. Okay, got it? Then, then we look at what's called X bar. I should have written that, which is just the average. And MR bar, which is the average of all the individual MRs. Okay, equals the average MRs. This is equal to the average of each of the X's. Okay, now this guy simply goes, let me do my palette here, green. There we go. This guy right here simply goes right here for the center line. Okay, got it? That's how that comes from. And now this guy, on the other hand, if we came up with, and I don't know what the answer is, but let's assume for just a moment that this process looks something like that the red lines would be for that. This does a little bit of a sidebar, and it goes to this. It turns out that 3 sigma is roughly equal to, put the plus or minus, equal to 2.66 mR bar. Okay? So 2.66 mR bar estimates plus 3 sigma, and that goes here and here. Okay? That's it. So again, if you're a green belt, you don't need to know the niceties of this calculation, and if you're a black belt, in the practical sense, it doesn't happen that much where you need to do it. We will cover it again in a later module when we do calculations of this sort. But for now, I just want us to be using this, and Excel Statistics or Minitab does this for you. So it's not a big deal. Okay, back to here. So that's what that MR bar is coming from, is this. So what happens if we take that point out? Well, one cool thing in Excel Statistics is if you go back to the data and we find that data point, which happens to be right there, we can see this first column where it says big X, little x. Sounds like Dr. Seuss, big X, little x, what begins with X. Well, it turns out that if we type in the big X, if you do that, hit the return, and then we'll go back to I, look what happened. It actually took that data point out, and it took it out of the calculation. If you'll notice, those are much tighter limits than we had before. We take that out just to demonstrate that. See how wide the limits are right there. And when we put in the big X, they're much tighter. Okay. Now you can also, you're wondering probably, what does little x do? Well, let's take a look. Here's what little x does. We put in little x. It tightens it up, but it takes it out of the calculation, but it leaves the picture of the limits in there. It leaves the data point in the picture. I like this a lot. I like this a lot because it demonstrates, first of all, it demonstrates that other than that point, it does look like it's a stable process. It doesn't necessarily mean that's a good process because, look, it's still 23% bad. 77% good means it's 23% bad. Most processes can't afford to be that bad. So this does say it's a stable process, but it doesn't say it's a good process. I want to be clear on that. It does say that the very first thing we ought to do is look into this data point and say, you know, why did we have this thing that was really out there? And only then, once we nail that, let's go ahead and systematically fix the rest of the stuff and maybe move the whole green line up as opposed to finding individual data points that are going to move it. Okay? All right. So that is that, and I'm going to leave this last, so there's this. I'm going to leave this last exercise as something for you to do on your own, and we'll finish up here. So I'd like you to take some time to fill out in your Lean Six Sigma journal, in your view, what are the takeaways of this section. I certainly have my takeaways, and what are the questions that you can answer, and finally, how you can support business improvement. I think it's important to look through all of those things every time, not just in a general sense, but go through every section. When you read those, fill them out, and that'll be something that you can go back to at the end, and it'll really help you understand what's the essence of what's going on for all these things. I do want to take a little bit of time and go back to my Blackboard and summarize what I think are some of the takeaways here. First of all, we talked about the voice of the process and the voice of the customer. That's a key concept. Okay, so the takeaways are that the control chart assesses the stability of a process. It is the voice of the process, not the voice of the customer. So because of that, we're looking at the data determining those red lines. It's the chart of choice should be the I chart for you. There's lots of different control charts as we saw in Minitab, but for now we're going to be choosing the I chart. I personally think that that's where you're going to end up with, too. But you'll need to know more of them later, particularly if you're a black belt. Key point in terms of interpreting a control chart is to look outside those plus or minus 3 sigma limits, which indicates a special cause, which means that before you do anything, you ought to dig in and check it out. And the main use of a control chart is to assess stability, and it can really help you stop fighting unnecessary fires. We all can use a little bit of that. We all could use a little bit of using our capacity, personal capacity and our staffing capacity more wisely. So thanks for listening. I appreciate it, and I hope you enjoyed the lecture, and I hope it helped out a lot.